What happens to a theory when the world moves on? Where do discarded ideas go when the last believer is gone? Can something sound brilliant and still be completely, utterly wrong? Science is often seen as a shining staircase, each step bringing us closer to truth. But that staircase is littered with abandoned scaffolds and crumbling concepts, each one once thought to be the key to understanding everything. One man who knew this all too well was Wolfgang Pauli, a physicist of dazzling intellect, but also of razor-sharp critique. Known for skewering sloppy theories with his legendary wit, he famously dubbed one young physicist's paper not incorrect, but not even wrong. A verdict so damning, so final, it left no room for redemption. And yet, most scientific theories don't need a Pauli to end them. Time does the work just as well. They fade, quietly. Once celebrated, once taught in lecture halls and scribbled across blackboards, now only ghosts in old textbooks. Take phlogiston, for example, once believed to be the essence of fire, the invisible substance released when things burned. For a time in the 18th century, it was the cornerstone of chemistry. But phlogiston never existed. It was a fiction, eventually replaced by the rise of real chemistry and atomic theory. Somewhere in history, the last scientist who truly believed in phlogiston passed away, and with them, the idea vanished. Or consider the great cosmological rivalry of the 20th century, the Big Bang versus the steady state. One spoke of a hot, dense beginning, the other of an eternal, unchanging cosmos, forever replenishing itself. For a while, both vied for supremacy. Even Einstein gave the steady state some thought. But the universe had other plans, and it was quasars, cosmic relics from the early universe, that whispered the truth. Slowly, the steady state flickered out. Today, a new frontier looms. We now chase the deepest of all mysteries, the unification of quantum mechanics and general relativity. Our best contenders, string theory and M theory, dizzying frameworks of hidden dimensions, vibrating filaments, and multi-dimensional brains. Conferences buzz, blackboards fill. Generations of physicists devote their lives to the dream. But the question remains, will these theories stand the test of time? Or will they too become footnotes, remembered not for what they explained, but for what they failed to become? Are they, in the end, not even wrong? The 5 string theories, a journey to the edge of fundamental reality. What does it mean for something to be fundamental? In physics, this term carries profound weight. It refers not simply to the smallest or most indivisible entities, but to the foundational principles and structures upon which all physical phenomena rest. To investigate this notion, let us embark on a conceptual journey inward, a voyage through the scales of physical reality, from the familiar world of humans, down to the potential bedrock of existence. Begin with our cells, bipedal members of Homo sapiens sapiens, typically standing just over 1.5 meters tall. This is our everyday scale, the anthropocentric reference point from which we measure the universe. Now, imagine compressing our field of vision by orders of magnitude. First, we descend to the scale of insects, small segmented organisms whose bodies span roughly 1 centimeter. This is a 100-fold reduction in scale. Zoom further to the cellular level. Cells, the fundamental units of biological life, typically measure a few micrometers in diameter, another factor of 10,000 smaller. At this level, we begin to glimpse the engine room of biology, mitochondria humming with chemical reactions, membranes orchestrating life's boundaries, DNA encoding the instructions of our form. But we do not stop there. Descend again by a factor of 1,000, and we reach the realm of molecules and atoms. Here, quantum mechanics begins to dominate. At distances on the order of nanometers and angstroms, less than a billionth of a meter, we see atoms bound by electromagnetic forces, electron orbitals shaping the geometry of molecules. the classical world begins to dissolve into a probabilistic fog. Continue inward. At the center of each atom lies the nucleus, a structure itself another 100,000 times smaller than the atom. Composed of protons and neutrons, each made up of even smaller constituents called quarks, the nucleus is held together by the strongest known force in nature, the aptly named strong nuclear force. This force binds quarks into nucleons, and nucleons into nuclei, operating at the scale of 1 femtometer, a million billionth of a meter. At this stage, we enter the domain of particle physics. The instruments we use to explore such minuscule realms, particle accelerators like the Large Hadron Collider, are among the most ambitious feats of human engineering. These colliders allow us to smash particles together at near light speeds and observe the fleeting traces of the fundamental forces at work. Through them, we can probe distances down to a few hundred atometers. But even the most powerful colliders yield to a barrier, the so-called Planck length. The Planck length, approximately 1.6 times 10 to the negative 35 meters, is theorized to represent a limit beyond which our current understanding of space and time ceases to apply. At this scale, general relativity, the elegant theory of gravity developed by Einstein, must confront the probabilistic chaos of quantum mechanics. It is here that physicists believe a new framework is required, a theory of quantum gravity. Enter string theory. String theory proposes that the ultimate constituents of matter are not point-like particles, but one-dimensional vibrating entities called strings. These strings oscillate at different frequencies, giving rise to the properties of particles, mass, charge, spin, as emergent phenomena of their vibration modes. According to the theory, strings may be either closed loops or open strands, and they exist not just in the familiar 4 dimensions of space-time, but in a higher dimensional space, often with 10 or 11 total dimensions, compactified in ways we cannot yet observe directly. Paradoxically, string theory was not originally conceived as a theory of everything. It began its life as a speculative model of the strong nuclear force. In 1968, a groundbreaking paper by Gabriele Veneziano introduced a mathematical formula that astonishingly matched experimental results for particle scattering. This formula hinted at an underlying string-like structure, and soon, theorists envisioned protons and neutrons as composed of vibrating strings rather than point particles. Excitement surged. The community paused, captivated by the beauty of the equations and their unexpected accuracy. For a moment, it seemed string theory might offer a unified description of nuclear interactions. Yet, the joy was short-lived. Experiments in the early 1970s revealed that protons and neutrons do not behave as expected under high-energy collisions if they were string-like. Rather than deforming and scattering softly, like gelatinous blobs, their behavior more closely resembled billiard balls rebounding with sharp impacts. The predictions of string theory were inconsistent with reality. By 1973, the theory was discarded as a candidate for explaining the strong force. In its place rose quantum chromodynamics, a successful and experimentally validated theory based on the exchange of gluons between quarks. String theory, it seemed, was dead. But in theoretical physics, intellectual death often precedes conceptual resurrection. Some researchers, most notably John Schwarz and Michael Green, recognized peculiar features in string theory that seemed too elegant to be coincidental. Among these was the natural incorporation of a particle with the properties of the graviton, a hypothetical quantum of gravity. Moreover, anomalies that typically rendered quantum theories inconsistent canceled out in string theory, but only in specific dimensions. In particular, string theory appeared consistent only in 10-dimensional spacetime, with 9 spatial dimensions and 1 temporal. Throughout the 1980s, these findings culminated in what is now called the first superstring revolution. String theory was reborn, not as a model for the strong force, but as a contender for the long-sought quantum theory of gravity. It promised not only to unify general relativity and quantum mechanics, but also to incorporate all other known forces, electromagnetic, weak, and strong, into a single framework. Physicists dared to dream. Perhaps string theory was the ultimate blueprint of reality. But then came an unexpected twist. Instead of a single elegant theory, string theorists uncovered 5 distinct and mathematically consistent string theories. Each operated in 10 dimensions and included supersymmetry, a symmetry that pairs bosons and fermions, but differed in key structural elements. The 5 theories are: Type 1, incorporating both open and closed strings. The presence of open strings allows interactions that resemble the electromagnetic, weak, and strong forces, while closed strings mediate gravity. Type 2a, a theory of closed strings with non-chiral supersymmetry, where the left and right moving vibrations on the string are symmetric. Type 2b, also involving only closed strings, but with chiral supersymmetry, distinguishing left and right moving modes. Heterotic SO32, a hybrid theory that combines left-moving strings from a bosonic theory with right-moving strings from a supersymmetric one, possessing a gauge symmetry group of SO32. Heterotic E8 times E8, similar to the above, but with a different gauge symmetry group. This version became especially prominent in attempts to relate string theory to observable particle physics. These theories differ in the types of strings they permit, the nature of supersymmetry they exhibit, and the symmetries of their internal spaces. Yet all are internally self-consistent. 5 logically distinct, yet viable theories, all in 10 dimensions, all incorporating gravity, and all arising from the same conceptual framework. For physicists seeking a unique and singular theory of everything, this proliferation was troubling. 5 is not 1. Even 2 would have been 1 too many. Was nature indecisive? Or were these seemingly separate theories different perspectives on a deeper, unified structure? This puzzle set the stage for the second superstring revolution of the mid-1990s, which introduced the concept of duality. Dualities are mathematical transformations that show how 2 apparently different theories are in fact equivalent when viewed from different vantage points, such as strong versus weak coupling, or small versus large compact dimensions. Through these dualities, the 5 string theories were shown to be interconnected, like the faces of a single multidimensional object. Moreover, an even more fundamental framework emerged, M-theory, which suggested that all 5 string theories are simply different limits of a more profound, 11-dimensional theory. In this view, strings are just one-dimensional slices of higher-dimensional objects known as branes. The journey inward, begun as a search for the smallest building blocks of matter, now touches the outer edges of a new conceptual frontier. String theory, with its promise and its puzzles, may not yet be the final answer, but it has reshaped the questions. In seeking the fundamental, we discovered that even the search for unity is a multifaceted endeavor, where the most profound truths may come not in solitary whispers, but in the harmonized vibration of many strings. One theory to rule them all, the emergence of M-theory. In an ancient Indian parable, a group of blind men encounter an elephant for the first time. Each man reaches out to touch the creature and describe what he feels. One grasps the trunk and declares it must be a serpent. Another touches the leg and likens it to a tree trunk. A third, feeling the tusk, proclaims it a spear or some war machine. Individually, their observations are coherent. Collectively, they are incomplete. none can perceive the full reality of the elephant, and so each mistakes a fragment for the whole. This parable, though simple, captures something profound about the nature of scientific inquiry, particularly the development of string theory in the latter half of the 20th century. By the mid-1980s, physicists had formulated 5 distinct yet mathematically consistent string theories, each offering a candidate for the unification of gravity with quantum mechanics. And yet the existence of 5 such fundamental theories posed a deep conceptual dilemma. Nature, it seemed, should be governed by a single, elegant framework. Were these 5 descriptions independent theories? Or could they represent different perspectives, partial glimpses of a deeper, more comprehensive structure? The answer would not fully emerge until 1995, when physicist Edward Witten unveiled a revolutionary new perspective that would forever alter the landscape of theoretical physics. What he proposed was startling in its ambition and coherence, that the 5 seemingly distinct string theories, along with an 11th dimensional gravitational theory known as supergravity, were merely boundaries, limiting cases of a single, unified framework. He called it M-theory. But before delving into Witten's breakthrough, it is worth revisiting the context from which M-theory arose. By the 1980s, string theory had matured from a failed model of the strong nuclear force into a leading contender for a unified theory of everything. It offered the tantalizing possibility of reconciling general relativity with quantum mechanics, a holy grail in theoretical physics. The theory posited that all fundamental particles were not point-like, but rather vibrational modes of tiny, one-dimensional strings. Yet there was a problem. Not 1, but 5 consistent string theories existed, each with unique properties. Type 1 contained both open and closed strings, with supersymmetry between fermions and bosons. Type Ia and Type Ib both involved only closed strings, but differed in their chirality, how left and right moving string modes behaved. Heterotic SO32 and heterotic E8 times E8, hybrids combining bosonic string modes on one side and supersymmetric modes on the other. Each theory existed in 10 dimensions and accommodated gravity through a massless spin-2 particle, identified with the graviton. But 5 fundamental theories? That was philosophically unsettling. As physicists, we seek unity, not multiplicity. If the universe is governed by a single set of physical laws, why should there be 5? The theories were too similar to be entirely independent, yet too different to be trivially equivalent. Like the blind man and the elephant, theorists suspected they were glimpsing only pieces of a deeper whole. The challenge was to find the coherent object they all described. Edward Witten was not always destined for theoretical physics. His academic journey began in history, and for a time, he even contemplated a career in politics. Yet his intellectual curiosity led him through economics and eventually into the realm of high-energy theoretical physics. What distinguished Witten was not merely his brilliance, but his fluency in 2 often disparate languages, mathematics and physics. Where physicists value physical intuition and conceptual flexibility, mathematicians prioritize rigor and precision. Witten bridged this divide with ease. By 1995, Witten had already transformed multiple fields, topological field theory, supersymmetry, and string theory among them. His work had earned him the Fields Medal, the most prestigious award in mathematics, making him the first and only physicist to do so. So when he stood before a packed audience at the Strings 95 conference at the University of Southern California, the room was electric with anticipation. Then came the revelation. The 5 10-dimensional string theories and 11-dimensional supergravity were not distinct theories at all. They were different approximations, limiting cases of a single, more fundamental theory. This theory, which had yet to be fully formulated, Witten dubbed M-theory. Witten's analogy was compelling. Imagine a vast unknown continent. On its periphery lie 5 coastal cities: Sydney, Adelaide, Perth, Darwin, Brisbane. Each city is unique, but all belong to the same underlying landmass. M-theory was the continent. The 5 string theories were its cities, situated at different boundaries. Supergravity was another outpost on this landscape. Between them stretched an interior, unexplored, complex, and rich with terrain, connecting each apparent theory into one unified whole. In technical terms, these connections were made possible by dualities, symmetries that relate seemingly distinct physical theories. Some dualities relate strong coupling to weak coupling. Others relate large spatial dimensions to small ones. These dualities suggested that what looked like separate theories were actually the same theory viewed from different physical regimes. But M-theory offered even more. It required 11 dimensions, not 10. This was surprising, since string theories had been developed explicitly in 10 dimensions. Yet the addition of one extra spatial dimension opened up new mathematical structures and fundamental objects beyond strings. Strings, Witten proposed, were not the most basic constituents of the universe. They were merely one-dimensional projections of higher-dimensional entities called brains. The word brain is derived from membrane, and it generalizes the idea of an extended object. A one-brain is a string. A two-brain is a membrane, a two-dimensional surface. A three-brain has 3 spatial dimensions, and so forth. Theoretically, M-theory accommodates brains of various dimensionalities embedded within an 11-dimensional spacetime. To understand this, imagine a string stretched taut between 2 points. This is a one-brain. Now, imagine a soap film stretched across a wire loop. This is a two-brain. Though our minds falter at visualizing higher dimensions, the mathematics handles such entities with ease. Crucially, brains under tension can wrap around small dimensions. If one of the 11 dimensions is compactified, curled up like a tiny circle, a two-dimensional brain could wrap around this circle. To a low-energy observer, it would appear as a vibrating one-dimensional string. Thus, in specific limits, M-theory reduces to string theory, and brains become strings. But in its full glory, M-theory is a higher dimensional theory in which brains, not strings, are fundamental. But how can extra dimensions, let alone wrapped brains, be real when we do not see them? To answer this, physicists often invoke the metaphor of an ant walking along a garden hose. To the ant, the hose is a one-dimensional path. It can move forward and backward, but the hose also has a circular cross-section. If the ant were small enough, or if its feet were sensitive enough, it might detect the curled-up second dimension and walk around it. To us, however, the circular dimension is invisible. We are simply too large and imprecise. In the same way, string theory and M-theory posit that 6 or 7 extra spatial dimensions exist, but they are compactified, curled up so tightly that we cannot detect them with current instruments. These hidden dimensions could be shaped in elaborate geometric forms, such as Calabi-Yau manifolds, which influence the behavior of particles and forces we observe in our 4-dimensional spacetime. Now add brains into this picture. Consider a two-brain wrapping around a tiny curled-up dimension, like shrink wrap folding around a wire. The surface tension causes the brain to conform tightly to the shape it encloses, effectively reducing its dimensionality. This process, called dimensional reduction, is central to how higher dimensional brains manifest as lower dimensional strings or particles in our universe. Thus, what appears as a string in 10-dimensional spacetime might actually be a tightly wrapped brain from an 11-dimensional M-theory framework. The implications of M-theory extend far beyond technical unification. They touch on the structure of the cosmos itself. Our universe could, in this view, be a 3-brain, a three-dimensional brain, floating in a higher dimensional bulk. Other brains might exist in parallel, perhaps containing entire universes with their own laws of physics. Moreover, the Big Bang might be reinterpreted as a collision between brains, cosmic objects crashing through higher dimensional space. Such ideas are speculative, yet mathematically plausible within the framework of M-theory. And so, the elegant simplicity of string theory yields to a richer and more mysterious vision of reality. A cosmos where dimensions, shapes, and extended objects intertwine in a higher dimensional dance, where strings arise not as primordial threads, but as shadows cast by deeper, multidimensional forms. Witten's proposal in 1995 did not conclude the story. It opened a new chapter. Much about M-theory remains unknown. No complete formulation exists. We do not yet possess a full set of equations describing its dynamics. And yet, the coherence of its implications, the power of its unifying structure, and the elegance of its geometric underpinnings offer a tantalizing glimpse into a deeper order of nature. In the end, M-theory may not be the final theory, but it reveals the terrain upon which such a theory might be found. Like the blind men groping at the elephant, we may still be feeling our way through fragmented understandings. But the shape of the elephant, the great coherent structure, has begun to emerge from the shadows. Whether M stands for mystery, magic, membrane, or simply the next letter in the alphabet after L for limit, remains unresolved. Perhaps the true meaning of M-theory, like the theory itself, awaits discovery. One that will finally link the elegant mathematics of higher dimensional brains to the burning stars and expanding galaxies we observe in the night sky. Brain cosmology, dimensions beyond the horizon? Consider for a moment the surface of a still pond. At times, tiny insects, water boatmen or backswimmers, can be seen skimming effortlessly across it, bound to the thin surface tension that supports their weight. They neither sink into the depths nor soar into the open air above. Their world, for all intents and purposes, is two-dimensional. They exist confined to a membrane, seemingly unaware of the vast three-dimensional environment that surrounds them. What if we are similarly limited in our perception? This analogy, modest yet profound, captures the central premise of brain cosmology. Just as the pond's surface defines the observable world for those insects, our own universe might be a three-dimensional brain embedded within a higher dimensional space. This possibility arises naturally within the framework of M-theory, the proposed unifying theory of all fundamental interactions that encompasses and extends the ideas of string theory. Within M-theory, extended objects called brains, short for membranes, occupy central roles. M-theory predicts not only two-dimensional M2 brains, but also five-dimensional M5 brains. When these higher dimensional entities wrap around compactified dimensions, especially the extra 11th dimension proposed by N-theory and the 6 curled-up dimensions from string theory, some physicists hypothesize that they could effectively manifest as three-dimensional surfaces. Crucially, such brains could be vast enough to contain an entire universe. In this conception, our universe is not the totality of all that exists, but rather a slice within a grander, higher dimensional reality. The fundamental forces described by the Standard Model, electromagnetism, the weak nuclear force, and the strong nuclear force, may be confined to this brain, their field lines limited to the three spatial dimensions we observe. Like ripples across the pond, these forces remain bound to the surface, incapable of escaping into the wider bulk. Yet gravity behaves differently. Unlike the other interactions, gravity in this framework is not restricted to the brain. Instead, its force lines, or more precisely, the gravitational field described by the curvature of spacetime in general relativity, can propagate into the higher dimensional bulk. This leakage provides a compelling explanation for the long-standing puzzle of gravity's relative weakness. The electromagnetic signals in your nervous system are powerful enough to lift a pen against the gravitational pull of the entire Earth, which weighs approximately 6 times 10 to the power of 24 kilograms. This extraordinary discrepancy in strength may be due to gravity's dilution across extra dimensions. While the other forces remain tightly localized to the brain, gravity spills into the higher dimensional space, weakening its apparent strength in our familiar three-dimensional world. Thus, brain cosmology offers a framework where the forced hierarchy problem, the striking difference in strengths among the fundamental forces, emerges not as an anomaly, but as a natural consequence of dimensional geography. But brain theories do more than address gravity. They have also been invoked in bold attempts to explain the origin and evolution of the universe itself. In some models of the early cosmos, brains play a dynamical role, moving and interacting within the higher dimensional bulk. One such scenario is known as brain inflation. Here, the inflationary epoch, a brief but astonishingly rapid expansion of space, believed to have occurred fractions of a second after the Big Bang, is driven not by a hypothetical scalar field, but by the motion and tension of brains. The tension associated with brains, immense in magnitude, could drive a repulsive gravitational effect, accelerating the expansion of space. As the brain traverses the bulk, this motion corresponds to the inflationary dynamics observed in cosmology. In this vision, the birth of the universe is not merely a singular explosion from nothing, but a grand unfolding, a higher dimensional geometry. An even more provocative model is the ekpyrotic scenario, in which the Big Bang is reinterpreted not as a beginning, but as a transformative event, a collision between brains. In this picture, a neighboring brain in the bulk approaches and collides with our own. The energy released in the collision seeds the universe with perturbations, slight irregularities, that, under the influence of gravity, evolve into the large-scale cosmic structures we see today. Galaxies, clusters, and filaments stretching across the observable universe. Such ideas are nothing short of extraordinary. They challenge the traditional narrative of cosmology and reframe our understanding of space-time. But they also demand an essential question. Why take these speculative constructions seriously? Why entertain the notion of invisible dimensions and unseen brains unless we have reason to believe they reflect reality? This is where brain cosmology meets a fundamental challenge of modern theoretical physics, the chasm between mathematical elegance and empirical validation. Every theoretical physicist eventually encounters a peculiar ritual, a thick envelope containing a self-published manuscript, usually accompanied by a handwritten letter declaring the discovery of a new theory of everything. Often, the writer claims to have corrected Einstein's errors. The contents, while passionate, are a morass of undefined symbols and disconnected assertions, a patchwork of ill-formed equations that fail even the most basic standards of logical coherence. As the physicist Wolfgang Pauli once quipped, such ideas are not even wrong, not simply incorrect, but lacking the internal structure required to be evaluated meaningfully. And this concern is echoed by skeptics of string theory and M theory alike. Are these frameworks so intricate, so beautiful, more than mathematical artistry? Are they themselves not even wrong, elaborate constructs without experimental anchor? There are, in truth, two notions of correctness at stake. The first and ultimate is empirical. Does the theory describe the real universe? Does it make testable predictions that can be verified by experiment or observation? In this regard, string theory and its extension into M-theory face formidable obstacles. As of today, there is no direct experimental evidence confirming any aspect of string theory, extra dimensions, or brains. Probing these regimes would require energies vastly beyond our technological reach. To appreciate the scale of this challenge, consider that the Large Hadron Collider, the most powerful particle accelerator built by humanity, reaches energies on the order of 10 to the 13 electron volts. Yet the energies required to probe string-scale physics are thought to lie around the Planck scale, approximately 10 to the 19 electron volts, a factor of 100 billion beyond current capabilities. Building an accelerator to reach such energies using present-day methods would require a ring extending well beyond Earth, perhaps as far as the orbit of Mercury. Such a project is for now a dream beyond engineering or economic plausibility. But there is a second, subtler sense of correctness: mathematical consistency. Even in the absence of experimental data, a theory can be evaluated based on its internal logic, its coherence, and its compatibility with known physics. Here, M-theory and brain cosmology fare better. They are built atop decades of cumulative progress in quantum field theory, general relativity, and topology. Concepts like perturbative finiteness, dualities, and supersymmetry are not merely jargon. They are essential mathematical properties that constrain the behavior of the theory in precise ways. Still, understanding these ideas demands deep expertise. From the outside, theoretical physics can resemble a linguistic battle of arcane terminology. How can one distinguish between an idea that is wrong and one that is simply misunderstood? When can we be sure that a theory is truly internally consistent and not merely elusive? Ultimately, in the absence of experimental access, physicists must cultivate a hybrid approach, balancing creativity with rigor, intuition with proof. Brain cosmology remains a speculative domain, but it is not arbitrary. It is shaped by an intense interplay between mathematics and physical reasoning, between bold imagination and unforgiving scrutiny. So, are brains real? Is M-theory a true description of nature or an elegant mirage? The answer is not yet known. But in the pursuit of such questions, physics performs its noblest function. It compels us to think beyond the visible, to question the familiar, and to imagine realities stranger and perhaps more beautiful than any we have yet observed. Proving the unprovable, duality, brains, and the deep structure of reality. Not far from the restless rhythm of New York City lies the hushed town of Princeton, home to ivy-covered walls and contemplative minds. Nestled at its outskirts, surrounded by forested serenity, stands the Institute for Advanced Study, an academic sanctuary unlike any other. Here, scholars are not encumbered by undergraduate lectures or lab supervision. Their currency is thought itself. The Institute has hosted some of the most luminous intellects in modern science. J. Robert Oppenheimer, the father of the atomic bomb, Freeman Dyson, architect of quantum electrodynamics, and perhaps most famously, Albert Einstein, who spent his final decades chasing the elusive dream of a unified theory. Einstein's later years were marked by a noble struggle to reconcile the forces of nature within a single framework, a quest that remained unresolved in his lifetime. Yet that ambition persists today. One of the Institute's contemporary torchbearers in this pursuit is the Argentinian theoretical physicist Juan Maldacena. Modest in demeanor, soft-spoken in delivery, Maldacena lacks the flamboyance often associated with revolutionary ideas. But in 1997, he proposed a theoretical framework so profound, it reshaped our understanding of gravity, space, and the very notion of dimensionality. At its core, lies a correspondence known as ADAS-CFT, short for anti-de Sitter, conformal field theory correspondence. The name itself is unassuming, technical, even forgettable, but beneath it lies one of the most powerful insights born from string theory in the past 3 decades. To comprehend its implications, we must return to the physics of brains. Brains, short for membranes, are multidimensional objects that arise in M-theory and string theory. In this framework, particles are not fundamental point-like entities, but rather one-dimensional strings, or higher-dimensional brains. Maldaceno's insight stemmed from exploring how physical laws manifest for an observer positioned close to such a brain. He envisioned 2 perspectives. First, consider an observer who lives on the brain, a hypothetical being confined to the brain's surface, much like a water boatman skating across a pond. To this observer, the laws of physics are dictated by the interactions and fluctuations within the brain itself. These might resemble, in form and content, the quantum field theories we use to describe fundamental forces, such as the strong interaction. Now, contrast this with a second perspective, that of an observer residing in the bulk, the higher dimensional space in which the brain is embedded. To this external viewer, the brain is not merely a flat surface, but a gravitational entity curving the surrounding spacetime. The physics, from this vantage, is governed by a higher dimensional theory of gravity, one that incorporates the brain not just as a locus of tension, but as a dynamic source of curvature. Here was Maldaceno's audacious proposition. Although the equations used by each observer, the one on the brain and the one in the bulk, appear entirely distinct, they describe precisely the same physical system. Every measurable quantity, every dynamic process, every correlation function that could be calculated in one description had a corresponding analog in the other. These 2 radically different formulations were, in fact, mathematically equivalent. This is what physicists call a duality, a concept that, like the Rosetta Stone, translates between 2 languages of physics. Just as ancient Egyptian hieroglyphs were deciphered by matching them with Greek and Demotic texts, a duality allows the same physical truth to be expressed through 2 dissimilar mathematical vocabularies. The ADS-CFT duality links a conformal field theory, a quantum field theory without gravity, living on a flat spacetime, with a gravitational theory defined in a higher dimensional anti-de Sitter space. It is a mapping from a 4-dimensional world without gravity to a 5-dimensional world with gravity, and, crucially, the 5th dimension corresponds to the radial, vertical distance into the bulk spacetime, perpendicular to the brain itself. One of the most compelling validations of this duality comes from a specific calculation. Physicists, working within the conformal field theory, computed an extraordinarily precise result, a quantity involving gauge interactions and quantum fluctuations. The mathematical structure was deeply non-trivial, so complex, in fact, that it defied the possibility of random coincidence. Then, astonishingly, the same quantity was computed using the gravitational theory in 5 dimensions. The results matched perfectly. Such a match is not a fluke. It signals a profound truth. 2 different paths through the jungle of equations lead to the same clearing. The 4-dimensional world of gauge theory and the 5-dimensional world of gravity, for all their surface differences, are shadows of the same deeper structure. But what does this mean physically? To appreciate the depth of Maldaceno's conjecture, one must understand a key feature of quantum field theories. Some are more quantum than others. In certain contexts, like the motion of a baseball or the trajectory of a planet, quantum effects are negligible. Classical physics suffices. Gravity, in particular, is a weak force whose quantum corrections are often imperceptibly small. However, in other domains, especially those governed by the strong nuclear force, quantum fluctuations dominate. The theories used to describe these regimes, like quantum chromodynamics, are non-linear and intractable by ordinary perturbative methods. Malvicina's duality flips this problem on its head. When the quantum field theory becomes strongly coupled and difficult to solve, its gravitational dual becomes weakly curved and easier to compute, and vice versa. In this way, gravity, often the most enigmatic force, becomes a tool to understand the least accessible regions of quantum field theory. It's as if two locked doors stand before us, one to the mysteries of gravity, the other to quantum fields. Maldacana's correspondence hands us a key that opens both. At first, the idea was met with skepticism. Could it truly be that a theory of gravity in 5 dimensions was equivalent to a theory without gravity in 4? Could such a strange symmetry be more than a formal coincidence? But over time, rigorous checks, detailed calculations, and mounting evidence silenced many doubters. What began as a speculative conjecture evolved into a cornerstone of theoretical physics. Importantly, this duality does not yet imply that M-theory or any string theoretic model is the definitive description of our universe. We still lack direct experimental confirmation. The ADS-CFT correspondence is most rigorously understood in special geometries, such as ADS spaces, that differ from the de Sitter geometry believed to describe our expanding cosmos. Yet what we do know is significant. The mathematical structure of string theory, with its branes, dualities, and higher dimensional formulations, is not nonsense. It is consistent, coherent, and predictive within its domain. Even if nature has chosen a different path, this body of ideas reflects a logic that is internally harmonious and stunningly elegant. So, is this the end of the line? Have we reached the final frontier of physics? Or is it possible that the path continues, spiraling deeper and deeper into more abstract territories? Layers of reality, stacked like Russian dolls, each embedded within the next. We do not yet know. Perhaps at the heart of matter are vibrating strings and higher dimensional branes. Perhaps the universe is a hologram with gravity emerging from quantum information encoded on lower dimensional boundaries. Or perhaps we are simply scratching the surface, our current models destined to be subsumed into grander syntheses. But this much is clear. The ADS-CFT correspondence and the web of dualities it reveals are not wild conjectures born of desperation. They are part of a robust theoretical edifice, one that hints at an underlying unity beneath the patchwork of known physics. It is an edifice built not on wishful thinking, but on rigorous mathematics, conceptual clarity, and a persistent search for truth. And so, in the woods of Princeton, in the quiet offices of the Institute for Advanced Study, the tradition continues. The drive to prove the unprovable is not hubris. It is a testament to the belief that reality, no matter how strange, is ultimately knowable. The equations may speak in many dialects, but their meaning, if we listen closely enough, remains one.
What if the ancient myths were more than just stories? What if, in their poetic descriptions of sun gods and celestial origins, they captured an essential truth about our existence? Could it be that, in some fundamental way, the sun truly is our God, not as a supernatural entity, but as the very source of our being? On the most basic level, the sun's radiant energy sustains life on Earth. Its warmth maintains temperatures within the critical range that allows liquid water to exist, creating the conditions necessary for biological processes. Photosynthetic organisms capture sunlight and convert it into chemical energy, fueling the intricate web of life. Every breath we take, every movement we make, is ultimately powered by solar energy transformed through countless biological interactions. Without the sun, Earth would be an icy, lifeless world adrift in the void. Yet, our connection to the sun runs even deeper. We are not merely recipients of its energy, we are, quite literally, built from the remnants of its cosmic ancestors. Just as ancient myths speak of sun deities born from primordial forces, our sun itself is a descendant of earlier stars. It was not the first of its kind, but a member of a long lineage of celestial bodies that have continuously shaped the universe. The sun emerged from a stellar nursery, a dense cloud of gas and dust pulled together by gravity. As matter accumulated, it compressed and heated until nuclear fusion ignited in its core, giving birth to the luminous sphere we see today. But where did this vast nebula come from? The answer lies in the life cycles of stars that came before. Our sun is classified as a population 1 star, meaning it was formed from the enriched remnants of older, now long extinct stars. These ancestors, population 2 stars, transformed the primordial hydrogen and helium of the early universe into heavier elements through nuclear fusion. In their final cataclysmic deaths as supernovae, they scattered these elements across space, seeding the next generation of stars. But even these were not the first stellar architects. Theoretical models predict the existence of an even earlier generation, the elusive population 3 stars, the first to ignite after the Big Bang. These stars, composed purely of hydrogen and helium, were colossal and short-lived, burning with an intensity that rapidly fused lighter elements into the building blocks of future celestial bodies. Though never observed directly, their fingerprints remain in the chemistry of ancient stars and the cosmic background radiation. Thus, our sun is the product of an ongoing cosmic cycle, a vast and intricate process of creation, destruction, and rebirth that has unfolded over billions of years. The elements that make up our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, were all forged in the hearts of stars long before our solar system even existed. Perhaps then the ancients were onto something. The sun is not just the center of our solar system, but a testament to the universe's grand design. It is the latest in an unbroken chain of cosmic fire, linking us to the very origins of matter itself. And so, in a way, the sun truly is our God, not in the form of myth, but as the ultimate source of life, energy, and existence itself. The alchemist's dream, from ancient transmutation to modern nuclear science. The year was 1782. In the hallowed halls of Great Britain's Royal Society, a claim emerged, one so audacious that, if true, it would resolve one of humanity's most enduring mysteries. A young and ambitious chemist, James Price, asserted that he had unlocked the secrets of transmutation, the fabled transformation of base metals into gold. Unlike the common charlatans who thrived on deception, Price presented empirical evidence, bolstered by experiments conducted before witnesses. His method, he claimed, involved the use of 2 mystical powders, a white powder that could turn mercury into silver and a red powder that could convert it into gold, producing an astonishing 60-fold increase in mass. While many of his contemporaries remained skeptical, his achievements did not go unnoticed. The University of Oxford conferred upon him an honorary medical degree, not explicitly for his experiments, yet the timing suggested a connection. To the public, it seemed that Price had finally proven alchemy to be a science rather than a fantasy. However, when the Royal Society pressed for a demonstration under its direct supervision, Price hesitated. He argued that the synthesis of these powders was so physically and financially exhausting that it rendered the entire process impractical. He insisted that his reputation as an honorable scientist should suffice to validate his findings. But in the face of mounting scrutiny, he relented. In January of 1783, Price stood before his esteemed peers, prepared to replicate his miracle. Yet, rather than performing alchemy, he consumed a vial of laurel water, rich in cyanide, and perished before their eyes. With his death, his secrets were lost, and his claim was cast into the realm of myth. Yet the desire to transmute elements did not die with James Price. It merely transformed. The dream of alchemy persisted, its spirit reborn in the crucible of modern physics. It was no longer gold that scientists sought, but a deeper understanding of matter itself. This quest would find its champion in a man who would revolutionize science, Ernest Rutherford. Born in 1871 in New Zealand, A remote British colony, Rutherford's brilliance propelled him from a single-room schoolhouse in Havelock to the hallowed halls of the University of Cambridge. At the turn of the 20th century, radioactivity was a nascent field, and Rutherford was among its earliest explorers. In his laboratory at McGill University in Canada, he and his colleague, Frederick Soddy, made a startling observation. Thorium, a heavy element, was spontaneously decaying into radium, a different element altogether. The implications were staggering. Soddy, in his excitement, proclaimed that they had discovered the secret of transmutation, the very goal of the ancient alchemists. But Rutherford, ever wary of the stigma attached to pseudoscience, cautioned him. For Mike's sake, Soddy, don't call it transmutation. They'll have our heads off as alchemists. Despite Rutherford's reluctance to embrace the language of the alchemists, their work marked a profound shift in scientific understanding. They had discovered that elements were not immutable. They could change, albeit not through magical powders, but through the hidden forces within the atom. By the 1920s, Rutherford had proven that elements could be intentionally altered. He demonstrated that by bombarding nitrogen atoms with alpha particles, energetic helium nuclei, he could produce hydrogen, an entirely different element. The experiment was further refined by Patrick Blackett, Rutherford's student, who used a cloud chamber to capture the moment of nuclear transformation. The photographic evidence left no doubt. Nitrogen had become oxygen. Blackett's work earned him the Nobel Prize in Physics in 1948, but the true revolution had already begun. Rutherford himself acknowledged the implications, remarking, "It is now possible by modern methods to produce exceedingly minute quantities of gold, but only by the transmutation of an even more costly element, platinum." Though his statement carried a touch of irony, it underscored a fundamental truth. Transmutation was real, but it was not economically viable. This newfound understanding of atomic structure would give rise to the most transformative scientific advancements of the 20th century. No longer were elements defined solely by their mass, as the ancients believed. Instead, the defining property of an element was its proton count, the number of positively charged particles in its nucleus. Change that number, and you change the element itself. Transmutation, therefore, could be achieved through several means. The first was through natural radioactive decay, in which an unstable nucleus emitted particles, thereby transforming into a lighter element. The second was through nuclear fission, in which a large atom, such as uranium, was split apart, a process harnessed for energy production and weaponry. The third was through nuclear fusion, the very process that powers the sun, wherein two smaller atomic nuclei merged to form a heavier element. Of these, fusion remained the most elusive and tantalizing goal. Nuclear fusion is the key to understanding the sun's extraordinary power. At its core, the sun fuses hydrogen atoms into helium, releasing an immense amount of energy in the process. This process is governed by two competing forces: the electrostatic repulsion between positively charged atomic nuclei and the strong nuclear force that binds them together. The strong force, though immensely powerful, operates only at extremely short distances. Overcoming the natural repulsion between atomic nuclei requires conditions so extreme that they are scarcely imaginable. Within the sun, where gravity exerts an unrelenting inward pull, fusion occurs at a relatively modest temperature of 15 million degrees Celsius. But on Earth, absent the sun's immense gravitational compression, scientists must generate temperatures exceeding 150 million degrees, 10 times hotter than the core of the sun, to force nuclei close enough for fusion to take place. The allure of fusion lies in its promise. Unlike fission, which produces long-lived radioactive waste, fusion generates immense energy with minimal byproducts. Its fuel, hydrogen isotopes such as deuterium and tritium, is abundant, extracted from water and lithium. If harnessed successfully, fusion could provide a virtually limitless, clean energy source. Yet, despite a century of research, controlled nuclear fusion remains just beyond our grasp. The technical challenges are monumental. Plasma, the high-energy state of matter required for fusion, must be confined and stabilized within a reactor. The most promising approach, magnetic confinement, relies on powerful electromagnetic fields to trap plasma within a toroidal chamber, such as those found in tokamak reactors. Another method, inertial confinement, involves compressing tiny fuel pellets with intense laser beams to induce fusion. Both techniques have yielded progress, yet neither has achieved sustained, net positive energy output. Still, the pursuit continues. In laboratories across the world, scientists refine their methods, inching ever closer to the dream of practical fusion energy. Projects such as the International Thermonuclear Experimental Reactor in France and the National Ignition Facility in the United States stand as testaments to human ingenuity and perseverance. The journey from alchemy to nuclear science is one of the most remarkable sagas in human history. What began as a mystical quest for gold evolved into a profound exploration of the fundamental nature of matter. Today, transmutation is no longer the work of alchemists, but of nuclear physicists. We can transform elements not through arcane rituals, but through our mastery of atomic forces. The ultimate triumph, however, lies ahead. The quest to harness the power of the stars continues, driven by the same relentless curiosity that once inspired the alchemists. As we stand on the brink of a new energy revolution, we are reminded of an age-old question posed by the great physicist Arthur Eddington. What is the source of the heat which the sun and stars are continually squandering? Fusion, the cosmic fire and humanity's pursuit of the stars. In the early 20th century, at the annual meeting of the British Association for the Advancement of Science in Cardiff, the English astronomer and physicist Arthur Eddington posed a deceptively simple yet profound question to his colleagues. What powers the sun? At the time, the prevailing wisdom among scientists attributed the sun's radiance to gravitational contraction, a theory holding that as the sun's immense gaseous mass collapsed under its own gravity, the compression generated heat, much as the young Earth had done when it first coalesced from cosmic debris. While this theory explained the immediate source of solar heat, it bore an inherent contradiction. By the early 20th century, geologists and physicists had established that the Earth, and by extension the solar system, was billions of years old. However, calculations showed that if the sun's energy derived solely from gravitational collapse, it would have burned out in a mere 20 million years. The theory, Eddington contended, was not merely outdated, it was a corpse that had yet to be buried. Seeking a new answer, Eddington turned to the emerging field of nuclear physics, pioneered by his contemporary, Ernest Rutherford. He theorized that the sun must be tapping into an unknown and vast reservoir of energy, an energy source that could only be subatomic in nature. He proposed that deep within the sun, hydrogen atoms were fusing into helium, releasing an extraordinary amount of energy in the process. More than just explaining stellar luminosity, Eddington's insight laid the foundation for modern astrophysics, revealing that stars were not merely celestial lamps, but cosmic forges responsible for creating the elements that constitute our universe. Eddington estimated that this nuclear process could sustain the sun for 15 billion years, a figure slightly high by modern standards, but conceptually correct. His work did not just provide an answer to the riddle of stellar power. It ignited a new question: could humanity harness the power of the stars? Over the past century, scientists have pursued that question with fervor, recognizing that nuclear fusion represents a potential key to an abundant, clean, and near-limitless energy source. Yet, as history has often shown, the mastery of such forces holds both the potential for prosperity and the peril of destruction. The lesson of the brown dwarfs, an alternative path to fusion. While our sun and other true stars achieve fusion through the intense pressures of their immense gravitational fields, they are not the only objects in the cosmos capable of nuclear reactions. Brown dwarfs, celestial bodies that exist in the liminal space between massive gas giants and the smallest stars, offer a compelling lesson in alternative fusion pathways. Too small to sustain the fusion of ordinary hydrogen, brown dwarfs instead undergo a different kind of nuclear reaction, one that relies on an isotope of hydrogen known as deuterium. Unlike protium, which consists of a single proton, deuterium possesses an additional neutron bound to the proton by the strong nuclear force. This extra neutron reduces the energy barrier required for fusion, allowing brown dwarfs to generate heat despite their lower mass. Deuterium is relatively abundant in Earth's oceans, where 1 in every 5,000 hydrogen atoms is a deuterium isotope. In contrast, in Jupiter's atmosphere, this ratio drops to 1 in 40,000, a figure closer to the natural cosmic abundance of deuterium. This property of deuterium, that it requires less energy to fuse than protium, has drawn the attention of scientists seeking to recreate stellar processes on Earth. If nuclear fusion is to become a viable energy source, humanity must find a way to exploit this unique isotope's potential. The National Ignition Facility, humanity's first glimpse at controlled fusion. One of the most ambitious attempts to achieve nuclear fusion on Earth has come from the National Ignition Facility in California. Here, scientists employ a novel technique to recreate the conditions necessary for fusion by targeting a tiny fuel capsule with an array of 192 ultraviolet lasers. The capsule, composed of synthetic diamond and cooled to temperatures just above absolute zero, is placed inside a golden cylinder no larger than a pencil eraser. In an instant, the lasers deliver an immense pulse of energy, causing the capsule to implode. This implosion generates the extreme temperatures and pressures necessary to trigger fusion, mimicking the energy dynamics found in brown dwarfs. At the heart of NIF's experiments lies the fusion of deuterium with tritium, a third isotope of hydrogen that contains 2 neutrons in its nucleus. When deuterium and tritium combine, they yield helium-4, the most abundant isotope of helium, and release an unbound neutron carrying 80% of the reaction's energy. In August 2021, NEF achieved a historic milestone. A single experiment fused approximately 200 micrograms of deuterium and tritium, momentarily generating a staggering 10 quadrillion watts of power, nearly 700 times the output of the entire United States electrical grid. However, this burst of energy lasted only 100 trillionths of a second and produced a net output sufficient to power a light bulb for just 6 hours. More importantly, the reaction reached 70% energy efficiency, edging ever closer to the long-sought goal of break-even, where energy output surpasses energy input. Despite this progress, 2 fundamental challenges remain. First, fusion reactions must generate more usable energy than they consume. Second, they must be sustained long enough to be practical for power generation. While NIF's method has shown promise, scientists continue to search for alternative approaches that can yield self-sustaining fusion reactions. The most ambitious project in the quest for nuclear fusion is the International Thermonuclear Experimental Reactor in France. Slated for activation in late 2025, ITER aims to be the first facility to produce net positive energy through fusion. The team behind ITER hopes to generate 10 times the energy input, demonstrating that fusion can be a viable power source. However, even if successful, ITER's energy output will not be captured for use. It will serve purely as an experimental proof of concept. Beyond deuterium-tritium fusion, alternative fuels such as helium-3 hold promise for a cleaner fusion process, producing fewer radioactive byproducts. Some scientists speculate that the Moon, after billions of years of exposure to the solar wind, may harbor significant quantities of helium-3. If so, future lunar missions may be tasked not just with exploration but with resource extraction, potentially igniting a new space race for fusion fuel. Long before the first stars, supernovae, or brown dwarfs began forging elements in their nuclear furnaces, there was a time when the universe itself was a fusion reactor. In the seconds after the Big Bang, as matter and energy condensed from the primordial chaos, nuclear fusion occurred on a cosmic scale. Hydrogen nuclei combined to form helium, and trace amounts of lithium and other light elements emerged. This brief but profound epoch, cosmic nucleosynthesis, set the stage for everything that followed, shaping the chemical makeup of the universe and enabling the eventual formation of stars, planets, and life. The pursuit of nuclear fusion represents humanity's attempt to reach back into this ancient, fundamental process and harness it for the future. As scientists continue their efforts to ignite a sustained fusion reaction, they are not merely seeking a new energy source, they are attempting to command the same cosmic fire that has shaped the universe itself. Whether this fire will illuminate a brighter future or serve as a force of destruction remains, as always, in humanity's hands. Big Bang nucleosynthesis, the cosmic alchemy that forged the first elements. If one were the 5th century BCE philosopher Empedocles, they might choose to hurl themselves into a volcano in an attempt to convince their followers of divine status. While this tale is likely myth, Empedocles is better remembered for a more enduring intellectual contribution, his efforts to define the fundamental nature of the universe. In his poem Periphysios, Empedocles introduced the idea that all substances in nature arise from a combination of 4 fundamental roots, a concept later adopted by Plato, who renamed them stoicheia, giving us the term elements. Though these ancient conceptions have long been superseded, they reflect a profound and enduring human desire to uncover the fundamental building blocks of existence. Today, we recognize 118 chemical elements, most of which are arranged within the periodic table in accordance with their shared properties. The heaviest of these elements, however, do not occur naturally in any significant abundance, as they decay too rapidly to persist. The elements that do comprise the observable universe have their origins in the tumultuous life cycles of stars. Through nuclear fusion in stellar cores, stars forge elements up to iron, but elements heavier than iron require more extreme processes, such as the cataclysmic death of a star in a supernova, or the gradual neutron capture within certain types of long-lived stars. Even more violent still is the collision of neutron stars, an event first directly observed in 2017 through gravitational waves detected by LIGO. When 2 neutron stars spiral into one another and merge, the resulting explosion, known as a kilonova, can synthesize and disperse an array of heavy elements. One such event provided direct spectroscopic evidence of strontium, atomic number 38, demonstrating that these cosmic cataclysms contribute to the elemental diversity of the universe. Yet before the first stars were born to forge heavier elements, before supernovae enriched the cosmos with their metallic remnants, there was an even earlier moment of elemental creation, one that unfolded within the first few minutes after the Big Bang itself. The most energetic moment in the history of the universe was its very inception, the Big Bang. In its immediate aftermath, the universe was an incomprehensibly hot and dense sea of fundamental particles, a primordial plasma governed by extreme temperatures and rapid expansion. Within the first microsecond, temperatures were still around 10 trillion degrees Celsius, conditions so intense that individual quarks, the fundamental constituents of protons and neutrons, could not yet bind together. But as the universe expanded, it cooled, eventually allowing quarks to coalesce into hadrons, forming protons and neutrons, the building blocks of atomic nuclei. Of the 6 known types of quarks, 2 dominate the everyday matter of our universe: the up quark and the down quark. The delicate balance of these quarks determines whether a hadron will become a proton or a neutron. Since hydrogen is defined by the presence of a single proton in its nucleus, the moment that protons emerged from the early quark soup was, in effect, the birth of hydrogen, the universe's first element. While neutrons were also initially present in equal abundance to protons, their slightly greater mass made them more susceptible to decay. Within a matter of minutes, neutrons were transforming into protons, electrons, and antineutrinos via beta decay. By the time the universe had cooled sufficiently for nuclear fusion to occur, the neutron-to-proton ratio had dropped to roughly 1:7, an imbalance that would go on to shape the elemental composition of the cosmos. The first step in nucleosynthesis, the process by which atomic nuclei form, was the creation of deuterium, an isotope of hydrogen consisting of 1 proton and 1 neutron. Though deuterium could, in theory, have formed immediately, the extreme temperatures of the early universe made its existence tenuous. High-energy photons were so abundant that any newly formed deuterium nuclei were quickly blasted apart. This phase, known as the deuterium bottleneck, temporarily stalled the formation of heavier elements. However, as the universe continued to expand, its temperature gradually fell. Around 300 seconds after the Big Bang, conditions had cooled sufficiently for deuterium to survive intact. At last, the bottleneck broke, and the universe could proceed with further nuclear fusion. Deuterium nuclei combined with protons and neutrons to form helium-3 and subsequently helium-4, the most stable and abundant isotope of helium. This process of Big Bang nucleosynthesis, first theorized in 1948 by Ralph Alpher and his mentor George Gamow, provided a theoretical foundation for understanding the universe's earliest chemistry. In their now famous Alpha Beta Gamma paper, Alpher described how the extreme conditions of the early universe could drive nuclear reactions, transforming hydrogen into helium and setting the stage for all subsequent stellar nucleosynthesis. Yet, while the process of fusion within stars can create a vast array of elements, the primordial Big Bang nucleosynthesis was constrained by a time-sensitive limitation. The universe was expanding and cooling too rapidly to allow the formation of elements heavier than lithium in any significant quantity. By the time the universe was mere minutes old, the temperatures required for fusion had already faded, leaving behind a cosmos primarily composed of hydrogen and helium, with trace amounts of lithium and beryllium. Though the universe was born with only a handful of elements, these primordial constituents laid the groundwork for everything that followed. The hydrogen and helium synthesized in the Big Bang would later coalesce under gravity to form the first stars, igniting nuclear fusion within their cores. These first-generation stars, known as population 3 stars, would burn brightly and die spectacularly, forging heavier elements in their fiery deaths and seeding the cosmos with the raw materials needed for planets, moons, and ultimately, life itself. From the violent chaos of the Big Bang to the intricate nuclear alchemy of stars and supernovae, the history of the universe is written in the language of element formation. The very atoms that make up our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, owe their existence to a chain of cosmic events set into motion nearly 14 billion years ago. And while the details of nucleosynthesis continue to be refined through astrophysical observations and theoretical advancements, one thing remains clear. The universe is, and always has been, an extraordinary factory of creation, assembling the fundamental ingredients of existence from the most extreme and beautiful forces nature has to offer. The cosmic forge, the end of Big Bang nucleosynthesis, and the seeds of a heavier universe. While hydrogen can exist without neutrons, helium cannot. The mutual repulsion of its two positively charged protons would make an isolated helium-2 nucleus an impossibility, as the electromagnetic force would overwhelm the nascent structure before it could even take hold. However, with the presence of just one neutron, the strong nuclear force, the fundamental glue of atomic nuclei, becomes sufficient to overpower this repulsion. The result is helium-3, a stable isotope formed in both the early universe and through modern cosmic processes, such as interactions with high-energy cosmic rays. Left undisturbed, helium-3 is effectively eternal, persisting until the end of time itself. Yet, the most abundant form of helium is not helium-3, but helium-4, an isotope composed of 2 protons and 2 neutrons. Its formation in the primordial universe was dictated by the same forces that govern the fate of all nucleosynthesis. The fusion of deuterium, with either helium-3 or tritium, provided the primary pathway for helium-4 synthesis, giving rise to the most stable composite nucleus known to physics. In nuclear physics, helium-4 is described as doubly magic, possessing a symmetrical arrangement of protons and neutrons that makes it exceptionally resistant to decay. This unparalleled stability made helium for the favored outcome of early nucleosynthesis. The universe, much like a great celestial alchemist, displayed a remarkable preference for its creation. Only protium formed in greater abundance. As a result, Nearly all available neutrons became locked within helium for nuclei, halting further nuclear progression. This early synthesis was not without constraints. The overall density of matter at the time dictated how much helium-4 could be produced. Had the universe been more compact during Big Bang nucleosynthesis, an even greater fraction of matter would have been funneled into helium, potentially altering the course of cosmic chemistry. In such an alternative scenario, the universe may have contained so much helium, an element chemically inert under normal conditions, that the very foundations of molecular complexity could have been stifled, rendering life as we know it impossible. Astrophysicists estimate that approximately 75% of the universe's baryonic mass after nucleosynthesis was locked in hydrogen with helium, for making up the remaining 25%. This fundamental ratio, exclusive of dark matter, neutrinos, and radiation, directly shaped the formation of the earliest stars, the elusive population 3 stars that astronomers continue to seek. Though hydrogen and helium formed the vast majority of matter, they are but 2 of the 118 elements known today. Where, then, did the remaining elements arise? The answer lies in the ticking clock of cosmic time as the universe continued to expand and cool. As nucleosynthesis proceeded, the next element in line was lithium, formed through the capture of additional protons. 2 isotopes emerged, lithium-6 and lithium-7, with the latter dominating in abundance. This was followed by beryllium, formed with 4 protons. However, beryllium-7, the only isotope created in significant quantities, was inherently unstable, decaying into lithium-7 within 53 days. An even greater challenge arose with the fleeting existence of beryllium-8. This isotope disintegrated almost instantaneously, within a billionth of a second, preventing it from serving as a stepping stone to heavier elements. In fact, no isotope composed of precisely 8 hadrons is stable, a fundamental roadblock in nucleosynthesis that prevented the formation of elements beyond lithium in any appreciable amount. At this point, the nuclear forge of the Big Bang began to sputter. With fewer heavy nuclei to facilitate further fusion, and with rapidly decreasing temperatures limiting reaction rates, the creation of elements with 9 or more nucleons became vanishingly rare. If any boron, carbon, nitrogen, or oxygen formed at all, it was in quantities so minuscule that no detectable trace remains in the cosmic record. 20 minutes after the Big Bang, the universe's first great act of creation came to an end. The nuclear fires that had spanned the entire observable cosmos cooled into stillness. At this moment, only 4 elements had been forged, and of those, only 3, hydrogen, helium, and lithium, persisted long enough to witness the birth of the first stars. It would take another 200 million years before conditions allowed for a second wave of element formation. As vast clouds of hydrogen and helium collapsed under the relentless pull of gravity, the first stars ignited in brilliant nuclear fusion. Their immense pressure and temperatures, far beyond anything seen in the early universe, would eventually give rise to heavier elements. But the story of those first stars, their origins, their properties, and their contributions to cosmic evolution remains an open question in modern astrophysics. In our attempt to reconstruct this ancient period of cosmic history, we are left with an unresolved enigma. Observations of the early universe, as inferred through studies of the oldest stars and the cosmic microwave background, suggest a discrepancy between predicted and observed abundances of lithium-7. This inconsistency, known as the cosmological lithium problem, remains one of the most significant outstanding challenges in Big Bang nucleosynthesis. In 2013, astronomers made an impossible measurement. Observations of ancient stars in the Milky Way's halo indicated that their lithium-7 content was significantly lower than theoretical predictions. Despite decades of refinements to nuclear reaction models and observational techniques, this discrepancy persists. Could our understanding of early universe nuclear physics be incomplete? Are there yet unknown processes that deplete lithium in these ancient stellar relics? Or does the answer lie in a deeper, more fundamental revision of the standard model of cosmology itself? The mystery lingers at the very heart of our understanding of the universe's first moments, an unresolved thread in the grand cosmic narrative. And so, as astrophysicists continue their search for population 3 stars and refine their models of nucleosynthesis, they are not merely probing the distant past. They are seeking to answer one of the most fundamental questions of all. How did the universe take shape, and what hidden forces continue to shape it today? The cosmological lithium problem, a scientific enigma at the dawn of time. Among the many celestial bodies that have captured the attention of astronomers, few are as paradoxical as HD 140283, a star that has been observed for over a century. When researchers finally attempted to determine its age with high precision, they were met with an apparent contradiction. This star seemed to be older than the universe itself. Initial calculations placed its age at approximately 14.5 billion years, a staggering result given that the widely accepted age of the universe is 13.8 billion years. Given its antiquity, the star was colloquially named Methuselah, after the biblical figure renowned for his longevity. Naturally, this age paradox pointed not to a flaw in the fundamental chronology of the cosmos, but rather to the limitations and uncertainties inherent in stellar dating techniques. Accounting for systematic errors and refining their models, astronomers subsequently constrained Methuselah's age to approximately 13.66 billion years, comfortably within the universe's timeline. More recent studies published in 2021 suggest it may be even younger, potentially as young as 11.5 billion years. While the exact age remains uncertain, the star's composition provides crucial insights into the early universe. By analyzing Methuselah's chemical makeup, astronomers concluded that it is not a first-generation star, but rather a member of the subsequent population 2 stars, objects that formed after the first stellar generation, known as population 3, had lived and perished. Unlike their predecessors, which contained virtually no elements heavier than helium, population 2 stars like Methuselah exhibit low but non-zero metallicity, approximately 0.1% of the Sun's. Over cosmic time, successive stellar generations enriched the interstellar medium with heavier elements, ultimately giving rise to population 1 stars, such as our Sun, which have metallicities exceeding 1%. The study of population 2 stars is crucial for testing theoretical predictions about the primordial universe. Since the most ancient stars are long gone, their chemical legacy persists as an imprint in stars like Methuselah, allowing astronomers to extrapolate back to the era of Big Bang nucleosynthesis, the period mere minutes after the Big Bang, when the first atomic nuclei formed. However, understanding these relics is not confined to individual stars. Astronomers also examine low-mass dwarf galaxies, which, due to their weak gravitational potential, retain a chemical signature closer to the primordial universe. These galaxies, having experienced relatively little star formation, provide an invaluable laboratory for studying the elemental abundances of the earliest epochs. Observations of ancient stars and low metallicity galaxies have largely confirmed the theoretical predictions of Big Bang nucleosynthesis for hydrogen, including its isotope deuterium, as well as helium-4. However, when it comes to lithium-7, a glaring discrepancy emerges. The observed abundance is only about 1/3 of what theoretical models predict. This puzzling inconsistency is what scientists have termed the primordial or cosmological lithium problem. The predicted abundance of lithium-7 is derived from a fundamental parameter, the photon-to-baryon ratio at the time of Big Bang nucleosynthesis. This ratio, independently confirmed by observations of the cosmic microwave background, should dictate the production of primordial elements with great precision. Yet, despite the consistency of hydrogen and helium measurements with theoretical expectations, lithium remains anomalously scarce. Scientists have proposed 3 primary explanations for this enduring enigma: stellar processes and observational biases. One possibility is that the lithium is not actually missing but rather concealed or destroyed in ways we have yet to fully account for. Stars, particularly old and hot population 2 stars, are highly efficient at depleting lithium through convective mixing and nuclear fusion processes. Given that astronomers can only observe a star's outer layers, it is possible that significant amounts of lithium are hidden beneath the photosphere. Additionally, uncertainties in temperature measurements can introduce systematic errors in abundance estimates, leading to potential miscalculations of the lithium content. Nuclear physics beyond current models. Another avenue of investigation lies in refining the nuclear physics governing lithium's formation. Lithium-7 primarily forms via the decay of beryllium-7. If the nuclear reactions that produce or destroy these isotopes operate slightly differently than current models suggest, it could help resolve the discrepancy. In 2015, a team of researchers reassessed the nuclear pathways of beryllium-7 formation and decay, yet their findings only deepen the inconsistency between theory and observation. New physics and cosmological implications. The most radical solution posits that our understanding of fundamental physics is incomplete. Theoretical predictions for primordial element abundances rely on our knowledge of the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear interactions, as well as the properties of elementary particles and the expansion history of the universe. If the early universe contained unknown exotic particles or interactions that altered nuclear reaction rates, this could provide an explanation. Additionally, the influence of dark matter or unknown variations in the early universe's density distribution might have subtly modified the synthesis of lithium. Another intriguing possibility is that our assumptions about the large-scale homogeneity of the cosmos are flawed. Cosmological models assume that the universe is statistically uniform on large scales, meaning that any observer, no matter their location, should infer the same fundamental properties of the universe. However, if our region of the cosmos is slightly underdense compared to the cosmic average, our local measurements could be biased, leading to discrepancies in inferred element abundances. Resolving the cosmological lithium problem remains one of modern astrophysics' great challenges. Future advancements in observational astronomy, particularly with next-generation telescopes capable of probing the chemical signatures of ever more distant and ancient stars, may help refine our understanding. Likewise, improvements in computational models and nuclear reaction measurements could either confirm or refute current theoretical frameworks. Ultimately, this puzzle is more than a mere technical anomaly. It is a potential window into undiscovered physics, the nature of the early universe, and the evolution of matter from the first instance after the Big Bang to the formation of galaxies, stars, and planets. Whether the solution lies in improved measurements, revisions to nuclear physics, or a profound shift in our understanding of cosmology itself, the answer will bring us one step closer to unraveling the mysteries of the cosmos. And so, we continue our journey, seeking to decode the fundamental narrative of our universe, from its fiery birth to the intricate cosmic structure we inhabit today.
What drives humanity to measure the world in extremes? Why are we so captivated by the fastest, the largest, the most powerful? This obsession with superlatives reflects our unending curiosity about the limits of nature, and it is through such pursuits that we have shaped and reshaped the course of history. Yet, in our quest for the ultimate, we have also created some of the most destructive forces imaginable. One such example is the Tsar Bomba, a testament to both human ingenuity and hubris. But even this colossal explosion pales in comparison to the forces at work in the wider cosmos. Let us embark on a journey from the depths of human ambition to the incomprehensible scale of stellar cataclysms, all bound by the enigmatic force of gravity. On October 30, 1961, a Tupolev Tu-95V bomber flew over Novaya Zemlya, an archipelago in the Arctic Ocean. Its mission was unprecedented, to unleash the most powerful man-made explosion in history. Suspended beneath parachutes to delay its descent, a 27-ton bomb nicknamed the Tsar Bomba fell gracefully toward the Earth. The delay was essential, giving the bomber time to escape the ensuing cataclysm. When the bomb detonated, it released a staggering energy equivalent to 50 megatons of TNT, 3,800 times more powerful than the bomb dropped on Hiroshima. The mushroom cloud soared 60 kilometers into the sky, and the flash was visible over 1,000 kilometers away. Heat from the blast caused third-degree burns to those within a 100-kilometer radius. This unparalleled display of power was both a political statement and a sobering reminder of humanity's destructive capabilities. However, in the same year, the cosmos unveiled a spectacle that dwarfed even the mightiest human invention. Astronomers observed the death of a star in a galaxy 45 million light-years away. This was a supernova, an event triggered when a massive star exhausts its nuclear fuel and collapses under its own gravity. With its core unable to resist the inward pull, the star implodes at a fraction of the speed of light, causing temperatures to soar and resulting in an explosion that scatters stellar material across light-years of space. The energy released by this single event is beyond comprehension, outshining entire galaxies. Yet, even the grandeur of a supernova is overshadowed by an even rarer phenomenon, the hypernova. These extraordinary explosions occur when stars more than 30 times the mass of our Sun meet their end. The star's core collapses to form a black hole, and the remaining stellar material ignites under the influence of extreme gravitational forces and searing winds of nickel-rich radiation. Hypernovae are up to 100 times more powerful than supernovae, representing the pinnacle of cosmic violence. They are the most energetic events in the observable universe, fueled by gravity's relentless pull. Despite the seemingly boundless power of these stellar events, gravity's influence is surprisingly weak when measured against the universe's other fundamental forces. There are four such forces: the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity. The strong nuclear force binds protons and neutrons within atomic nuclei, making it the strongest of the four. The electromagnetic force governs interactions between charged particles and enables the radiation that lights and warms our universe. Even the weak nuclear force, which facilitates radioactive decay and stellar fusion, vastly outmatches gravity. In fact, gravity is weaker than the weak force by a factor of 10 to the 25th power, 10 trillion times. This apparent weakness poses a profound mystery, known as the hierarchy problem. How can gravity, so feeble at atomic scales, dominate the universe at large? To feel its effects, we require enormous accumulations of matter, such as planets, stars, and black holes. A simple ant, using the chemical energy in its legs, can defy the gravitational pull of an entire planet. Yet, when matter aggregates on a cosmic scale, gravity shapes the structure of galaxies, governs the orbits of celestial bodies, and even dictates the flow of time itself. The enigma of gravity's weakness has led physicists to propose extraordinary explanations. Some theories suggest that gravity's effects are diluted because it extends into dimensions beyond the familiar three of space and one of time. These additional dimensions, if they exist, could hold the key to understanding gravity's place among the fundamental forces. To unravel these mysteries, we must look to the earliest moments of the universe. In the seconds following the Big Bang, the fundamental forces were unified. As the universe expanded and cooled, they separated, a process that shaped the cosmos as we know it. The study of this period could provide insights into the origins of gravity and its apparent disparity with the other forces. Moreover, experiments at the frontiers of particle physics, such as those conducted at the Large Hadron Collider, aim to probe the nature of gravity and its relationship to the quantum realm. These investigations may uncover evidence of extra dimensions or reveal particles associated with gravity, known as gravitons. Such discoveries would revolutionize our understanding of the universe's fundamental structure. The quest to understand gravity is not merely an academic pursuit. It is a journey that touches on the very fabric of existence, from the smallest particles to the largest galaxies. Gravity shapes our daily lives, keeps our feet on the ground, and challenges our engineers as they reach for the stars. It binds the universe together, yet its true nature remains elusive. As we gaze upon the remnants of supernovae and hypernovae, and as we study the colossal black holes at the hearts of galaxies, we are reminded of gravity's dual nature, at once unimaginably powerful and deceptively weak. It is a force that defines the cosmos yet humbles us with its mysteries. To truly understand it, we must look beyond our own world, to the distant stars and the origins of time itself. Only then can we hope to grasp the full scope of this most fundamental of forces. Why do we fall? Gravity, the first of nature's forces to be recognized and quantified by science, is both the most familiar and the most enigmatic. For all its universality, gravity continues to defy complete understanding, eluding the grasp of even the most brilliant minds in history. To unravel its mysteries is to embark on a journey through the centuries, from the orchards of 17th century England to the curved geometries of spacetime, and onward to the frontiers of modern physics. The tale begins, as so many scientific odysseys do, with Isaac Newton. A solitary and meticulous man, Newton was as reserved in his personal life as he was prolific in his intellectual pursuits. The legend of his epiphany beneath an apple tree has become as much a part of scientific folklore as gravity itself. Whether or not an apple ever truly struck the ground before his contemplative eyes, the story captures the essence of Newton's genius, his ability to see the profound in the mundane. In 1666, during a plague-induced closure of Cambridge University, Newton retreated to his family home in Lincolnshire. There, in the quiet isolation of Woolsthorpe Manor, he laid the groundwork for his theory of universal gravitation. Why should that apple always descend perpendicularly to the ground, he wondered, as he later recounted. This simple question led him to imagine an invisible force extending beyond the Earth's surface, reaching across the heavens to bind the moon in its orbit and guide the planets on their celestial paths. Newton's formulation was elegantly simple. Every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. This universal law of gravitation proved astonishingly effective. It explained the motions of the planets, the behavior of tides, and even the trajectories of comets. Yet, for all its predictive power, Newton's theory left unanswered the fundamental question: what is gravity? Newton himself was acutely aware of this limitation. That gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it, he wrote. While his equations worked, he could not fathom how one object could exert a force on another across empty space. Newton's reluctance to ascribe an intrinsic nature to gravity reflected his scientific humility and presaged the challenges that would confront physicists in the centuries to follow. For 200 years, Newton's theory reigned supreme. It guided explorers across uncharted oceans, enabled the construction of mechanical wonders, and illuminated the dance of celestial bodies. Yet, as observational techniques grew more sophisticated, cracks began to appear in its foundation. The orbit of Mercury, for instance, deviated ever so slightly from Newtonian predictions. This wobble, or precession, hinted at forces beyond the scope of classical mechanics. The turn of the 20th century brought with it a revolution in physics. Albert Einstein, a German-born physicist with an uncanny ability to see the universe in ways no one else could, turned his attention to the shortcomings of Newtonian gravity. Building on the insights of special relativity, Einstein proposed a radical new framework, general relativity. At its core was a simple yet profound idea: gravity is not a force in the traditional sense, but a manifestation of the curvature of spacetime. To grasp this concept, imagine a heavy object placed on a taut rubber sheet. The weight of the object distorts the sheet, creating a depression. Smaller objects placed on the sheet will naturally roll toward the center of the depression, not because they are being pulled, but because they are following the contours of the curved surface. Similarly, Einstein argued, massive objects like stars and planets warp the fabric of spacetime, and it is this curvature that guides the motion of objects within it. Einstein's theory was as mathematically intricate as it was conceptually revolutionary. It predicted phenomena that Newtonian gravity could not explain, such as the bending of light around massive objects and the precise precession of Mercury's orbit. These predictions were spectacularly confirmed during a solar eclipse in 1919, when astronomers observed starlight curving around the Sun exactly as Einstein had calculated. General relativity not only supplanted Newtonian mechanics but also opened the door to a universe far stranger than anyone had imagined. Yet, for all its triumphs, general relativity left its own set of mysteries in its wake. While it described the behavior of gravity on cosmic scales with unparalleled precision, it offered little insight into its origins. Why does gravity exist? Why is it so weak compared to the other fundamental forces? And how does it reconcile with the quantum realm, where the rules of physics take on an entirely different form? The weakness of gravity is one of the most perplexing puzzles in physics. Compared to the strong nuclear force, which binds protons and neutrons within atomic nuclei, gravity is astonishingly feeble. To put it in perspective, the electromagnetic force between two electrons is about 10 to the power of 36 times stronger than the gravitational attraction between them. This disparity, known as the hierarchy problem, suggests that we are missing a crucial piece of the puzzle. One possibility is that gravity operates on a fundamentally different plane than the other forces. Some physicists speculate that it may leak into extra dimensions beyond the familiar 3 of space and 1 of time. These hypothetical dimensions, though hidden from everyday experience, could dilute gravity's effects in our observable universe. Experiments at facilities like the Large Hadron Collider are probing these ideas, searching for evidence of gravitons, theoretical particles associated with gravity, or subtle deviations from the inverse square law at microscopic scales. Another avenue of exploration lies in the early universe. In the moments following the Big Bang, the 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are believed to have been unified. As the universe expanded and cooled, they separated, each taking on its distinct characteristics. Understanding this process could shed light on gravity's true nature and its role in the cosmos. Despite decades of effort, the quest to unify general relativity with quantum mechanics remains one of the greatest challenges in theoretical physics. The two frameworks are mathematically incompatible, yet both are essential for describing the universe. While general relativity governs the behavior of massive objects and the structure of spacetime, quantum mechanics dictates the interactions of particles on the smallest scales. Bridging this divide may require a paradigm shift as profound as Einstein's reconceptualization of gravity a century ago. One promising candidate for such a unifying theory is string theory, which posits that all particles are not point-like but rather tiny vibrating strings. These strings exist in a multidimensional spacetime, and their vibrations give rise to the fundamental forces and particles we observe. String theory suggests that gravity arises naturally within this framework, offering a tantalizing glimpse of how the quantum and cosmic realms might be reconciled. However, it remains a deeply mathematical and experimentally unverified construct, as elusive as the nature of gravity itself. In the meantime, gravity continues to humble and inspire us. It shapes the galaxies, governs the orbits of planets, and choreographs the intricate ballet of celestial bodies. It binds us to the earth, enabling the simplest pleasures of walking and running, and challenges us to reach for the stars. From the fall of an apple to the bending of starlight, gravity's story is one of discovery and wonder, a testament to humanity's enduring curiosity about the universe. As we stand on the precipice of new discoveries, the questions that Newton and Einstein grappled with remain as relevant as ever. Why do we fall? What is the nature of the force that binds the cosmos together? To seek these answers is to confront the very fabric of reality, to delve into the origins of existence, and to marvel at the profound simplicity and complexity of the universe. Gravity, the silent architect of the cosmos, awaits our understanding, a challenge that beckons us to explore, to question, and to dream. Ripples from the beginning of time. To detect ripples in the very fabric of space that have traveled across the cosmos for billions of years? Such questions evoke a profound sense of wonder, pushing the boundaries of our imagination as we attempt to understand the origins of our universe. These ripples, gravitational waves, carry whispers from the birth of the cosmos, offering us glimpses into epochs long before stars and galaxies existed. To follow their journey is to trace the history of existence itself, from cataclysmic collisions to the enigmatic beginnings of spacetime. A billion years ago, the Earth was a quiet, unchanging world. The planet languished in a geological and evolutionary stasis that scientists call the boring billion. Life, once brimming with innovation, had stalled. The planet's chemistry, climate, and geography appeared frozen, offering no clue of the monumental cosmic events occurring far beyond Earth's skies. In a distant region of the universe, two black holes, each over 30 times the mass of our Sun, were locked in an inexorable dance. Spinning ever faster, their violent embrace culminated in a collision so powerful it sent ripples through spacetime itself. These gravitational waves raced outward at the speed of light, carrying with them the energy of a cataclysm whose magnitude defies comprehension. But for over a billion years, these ripples passed unnoticed through the universe. Their arrival on Earth came not during the boring billion but in an age of human ingenuity. On September 14, 2015, a revolutionary instrument known as LIGO, Laser Interferometer Gravitational Wave Observatory, detected these waves. Just 2 days after being activated, LIGO recorded a fleeting signal, a chirp lasting less than a fifth of a second. This signal was the faint echo of the black hole collision, reaching Earth after a journey of cosmic proportions. LIGO's achievement was nothing short of extraordinary. For decades, skeptics doubted whether gravitational waves, predicted by Einstein's general theory of relativity in 1915, could ever be detected. Einstein himself was unsure if such waves, distortions in spacetime caused by massive gravitational disturbances, would be measurable. LIGO overcame these doubts by using lasers to detect minute changes in the lengths of its arms, changes smaller than the width of a proton. When a gravitational wave passed through the observatory, it subtly altered the distance between mirrors placed kilometers apart, producing the unmistakable chirp that heralded the arrival of waves from a billion-year-old event. This discovery was not just a technical triumph, it was a new way of observing the universe. For centuries, astronomers relied on light, visible, infrared, and other wavelengths to study the cosmos. But light can be obscured or absorbed, limiting our view of the universe's most extreme events. Gravitational waves, however, penetrate all matter unimpeded, carrying information from the darkest and most distant corners of existence. LIGO's detection opened a new window on the cosmos, allowing scientists to hear the universe for the first time. Subsequent discoveries confirmed the power of this new tool. In 2017, LIGO detected gravitational waves from a pair of merging neutron stars. This event produced not only gravitational waves but also gamma rays and visible light, enabling astronomers to observe it across multiple wavelengths. Such multi-messenger astronomy confirmed the violent origins of heavy elements like gold and platinum, forged in the aftermath of neutron star collisions. These discoveries validated Einstein's predictions and solidified LIGO's place in scientific history, earning its researchers the 2017 Nobel Prize in Physics. Yet, these detections only scratch the surface of what gravitational waves can reveal. They provide insights into the fundamental nature of gravity, a force that permeates the universe yet remains profoundly mysterious. Gravitational waves demonstrate that gravity is not an instantaneous pull between objects, as Newton envisioned, but rather a field that can ripple and carry energy through spacetime. This means that changes in a gravitational field propagate at the speed of light. If the Sun were to vanish, Earth would continue orbiting for 8 minutes, the time it takes for the information to reach us. Such revelations align gravity with the other fundamental forces of nature, electromagnetism and the strong and weak nuclear forces, which also operate as fields with wave-like properties. Light, for instance, is a ripple in the electromagnetic field. By studying gravitational waves, scientists hope to uncover connections between gravity and these other forces, potentially leading to a unified theory of physics. One tantalizing possibility is the detection of primordial gravitational waves, ripples generated during the universe's earliest moments. Current cosmological models suggest that the universe underwent a period of rapid inflation shortly after the Big Bang, expanding exponentially in less than a fraction of a second. This inflation would have generated gravitational waves, encoding information about the universe's infancy. These primordial waves would have traveled through spacetime for 13.8 billion years, reaching us as faint whispers from the dawn of time. Detecting such waves is a formidable challenge. LIGO and its successors, like the European Space Agency's planned Laser Interferometer Space Antenna, LISA, are being designed to filter out the noise of more recent cosmic events. LISA, with its kilometer-scale arms positioned in space, aims to detect waves from the universe's earliest epochs, providing unprecedented insights into the nature of inflation and the origin of gravitational fields. The detection of primordial waves could confirm key assumptions about the universe's birth. For instance, gravitational waves could reveal whether inflation was a gradual process or a sudden, violent event. They could also shed light on the nature of the gravitational field itself. Unlike the Higgs field, which gives particles mass, gravity is linked to energy and momentum. This distinction means that gravity could have existed even before the Higgs field emerged, influencing the universe long before matter acquired mass. Indeed, most cosmologists believe that gravity emerged during the Planck epoch, the earliest phase of the universe, when spacetime was compressed to scales smaller than a proton. At such scales, the classical laws of physics break down, and quantum effects dominate. Understanding gravity in this regime requires uniting general relativity with quantum mechanics, a goal that has eluded physicists for decades. New theories, such as string theory and loop quantum gravity, offer tantalizing possibilities. These frameworks suggest that spacetime itself may have a discrete, quantized structure, and that gravity arises from fundamental vibrations or connections at this microscopic level. While these ideas remain speculative, they highlight the profound connections between gravity, the fabric of spacetime, and the origins of the cosmos. Leaving our dimension. Lisa Randall's journey through Yosemite offers a striking metaphor for the forces that govern our universe. As she climbed the sheer rock face, she grappled with gravity, a force so weak that a single rope could suspend her against its pull, yet so unyielding that it accelerated her descent with unforgiving precision when her grip faltered. This duality of gravity's weakness and persistence mirrors its enigmatic nature in physics, the least understood of the fundamental forces, yet essential in shaping the cosmos. At the heart of our struggle to comprehend gravity lies a profound incompatibility between the two pillars of modern physics. General relativity, Einstein's masterpiece, describes gravity as the curvature of spacetime, a framework that elegantly explains the behavior of massive objects and the large-scale structure of the universe. Quantum mechanics, on the other hand, delves into the subatomic realm, where particles and forces obey probabilistic rules that defy classical intuition. Despite their individual successes, these theories clash irreconcilably when applied together, particularly at the Planck scale, a realm so minuscule that the distinctions between space, time, and energy blur. Most forces in nature, such as electromagnetism and the strong and weak nuclear forces, have been successfully integrated into the quantum framework. Each is mediated by messenger particles, photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. These particles arise from quantized fields that permeate the universe, their interactions governed by the elegant mathematics of quantum field theory. Gravity, however, remains the exception. Theoretical physicists have long posited the existence of a quantum particle called the graviton, a carrier of the gravitational force. Yet, detecting such a particle has proven elusive. The graviton's faint signal would require an impossibly large detector, one with a diameter surpassing that of our solar system, to measure its effects with precision. Complicating matters further, attempts to quantize gravity lead to mathematical divergences. When energy and momentum distort spacetime at quantum scales, the resulting feedback loop generates infinite energy densities that cannot be renormalized, a cornerstone technique used to tame infinities in other quantum fields. This failure suggests that our current frameworks are inadequate for describing gravity at the smallest scales. To address these challenges, physicists have proposed radical new theories. Loop quantum gravity reimagines spacetime not as a continuous fabric but as a network of discrete loops, each woven into a fine lattice at the Planck scale. This approach avoids the infinities that plague traditional models, treating gravity as an emergent property of spacetime geometry rather than a force in the classical sense. While promising, loop quantum gravity lacks the experimental evidence needed to confirm its validity. String theory offers another paradigm, envisioning the fundamental constituents of reality as tiny vibrating strings existing in a multidimensional space. In this framework, the three spatial dimensions and one temporal dimension we experience are merely emergent properties of a larger, more complex reality. String theory elegantly accommodates gravity, suggesting that its weakness arises from its connection to these hidden dimensions. Specifically, gravity's effects may be diluted as it propagates through additional spatial dimensions beyond our perception. Here, Lisa Randall's work enters the stage. Her groundbreaking theories extend the idea of multidimensional space, proposing that our universe is a three-dimensional brane embedded within a higher-dimensional bulk. In this model, the other fundamental forces are confined to our brain, while gravity resides primarily in a separate brain. The interactions we observe are merely the leakage of gravity from this gravibrane into our universe, explaining its apparent weakness. Randall and her collaborator Raman Sundram devised a mathematical framework to support this idea, showing that warp geometries in higher dimensional space could account for gravity's exponential decay across the bulk. This approach resolves the inconsistencies of supersymmetry, a theory that predicts partner particles for every known particle but struggles to align with observational data. By situating gravity in a separate brane, Randall and Sundram preserved the elegance of supersymmetry while reconciling it with reality. The implications of Randall's theories are profound. If gravity truly originates in another dimension, it may never be fully detectable within our own. The elusive gravitons sought by particle physicists might simply have an infinitesimal probability of straying into our universe, making their detection a matter of extraordinary luck. Yet, the tantalizing possibility of higher dimensions reshapes our understanding of the cosmos, offering a glimpse into realities beyond our own. Despite its elegance, Randall's work, like all theories of quantum gravity, remains speculative. The mathematical consistency of her models is compelling, but experimental validation is essential. Just as gravitational waves were once dismissed as theoretical curiosities until LIGO's groundbreaking detection, so too might these multidimensional theories await their moment of empirical vindication. To this end, physicists around the world are developing instruments and experiments to probe these possibilities. Particle accelerators, such as the Large Hadron Collider, continue to search for evidence of supersymmetry in extra dimensions. Meanwhile, gravitational wave observatories and next-generation detectors like the Laser Interferometer Space Antenna aim to uncover new insights into the nature of spacetime itself. As Randall's theories remind us, the universe is far more intricate than it appears. From the immensity of galactic structures to the subatomic dance of particles, every level of reality is interwoven with mysteries that challenge our intellect and imagination. Gravity, the silent architect of the cosmos, may hold the key to unlocking these secrets. Whether its origin lies within our universe or beyond it, the quest to understand gravity is a journey that transcends dimensions, inviting us to explore the very foundations of existence.